Okay, great. So the next talk will be given by Zhenning Liu from the University of Maryland, and he's going to talk about efficiently verifiable quantum advantage on near-term analog quantum simulators.
All right. Thanks a lot for the introduction. So today I'm going to talk about efficiently verifiable demonstration of quantum advantage on near-term analog quantum simulators. And this is a joint work with a group of people at the University of Maryland working on this topic of verified quantum simulation. So what is a demonstration of quantum advantage? In my opinion, this is a game between a classical verifier and an untrusted self-claimed quantum prover. So in this game, the prover aims to show to the verifier that he indeed has some quantum computational power, and the verifier needs to determine whether this is true or not. So there are several examples of demonstration of quantum advantage. The most conceptually easy one is using the factoring problem. The verifier can just generate a large integer and send it to the prover. If the prover can factorize it very, very efficiently, like using Shor's algorithm, then of course the prover has some super strong computational power. However, this method requires the prover to perform Shor's algorithm that is not near-term feasible, unfortunately. So there are some other ideas like this cryptographic proof of quantumness, which is basically a test that can only be passed by evaluating a cryptographic function in superposition. So this is easier than performing the Shor's algorithm, but unfortunately it's still not very near-term feasible. The third idea is based on this random circuit sampling, which is basically the measurement outcomes from these random circuits are from some classically hard distribution. So this is a very famous idea because it has been experimentally realized in this very famous results in Nature in 2019. But unfortunately, it is inefficient to verify or benchmark the results of the sampling. So it generally takes exponential time for you to verify if it's true or not, if it's correct or not. So it seems pretty hard for us to have all of these good features under this framework of demonstrating quantum advantage at the same time. So we start to think, what if we take a step back and give the prover a little bit of trust? So it's no longer fully untrusted, but with some other trust that we can give him, like trusted measurements. So to talk about what is trusted measurements and why it is useful, I want to first introduce a classically hard IQP sampling problem, which is also the problem that we will be relying on in designing our quantum advantage protocol. We take this result from the Bermeo-Vega et al. Paper in 2018. So in this problem, we have n qubits. They are on a 2D square lattice. The initial state of the system is denoted by phi naught, in which it is just a product state, and each qubit state is randomly sampled from the plus state or the plus state with a fixed relative phase, which is pi over 4. The system is also equipped with a Hamiltonian that is a ZZ plus Z nearest neighbor uniform Hamiltonian. So it's quite easy to represent Hamiltonian. It's just the sum of all the ZI-ZG terms and the sum of ZI terms, and all the coefficients are just pi over 4. So the result of this Bermeo-Vega et al. Paper and the Rainbow et al. Paper are that we let P be the distribution of all the X basis measurement outcomes on the state that is e to the minus IH acting on the phi naught. That is basically the input state while going through some unit time Hamiltonian evolution, where the Hamiltonian is just the ZZ plus Z Hamiltonian. Then the X basis measurement outcomes from this state are in the distribution P, and the sampling from this P distribution within some constant total variation distance, or TVD, it's hard for classical computation under some plausible computational assumptions. So you can also easily see a corollary of this result. That is, if the noise rate in the measurements is known to be tiny, then if the state, which is the output state, is prepared with fidelity higher than some threshold fidelity, then we can also say quantum advantage exists in this state. Okay, so now we can easily design a simple scheme of verification of demonstrating quantum advantage based on this problem. We can just ask the prover to prepare the output state, that is the time-evolved input state, and then measure it in the X basis and then send the outcomes to the verifier. However, this will be the same as very similar to the random circuit sampling, because it generally takes exponential time to verify if the samples are from the hard distribution or not. Or we can also maybe check if the fidelity of the output state is big enough or not, but unfortunately this is also inefficient or impractical if only classical communication is allowed. So this means that we probably need to relax our game rules. A commonly used model in computer science is to allow the verifier to send or to measure the state by herself. But in this case, the quantum state must be transmitted from the prover to the verifier. But it is very hard for us to imagine this is feasible in the near term, especially for like a large number of qubits. So we come up with an equivalent scheme of this state transmission. That is, the verifier trusts the prover for measuring every prepared state in the basis given by the verifier with noise rate lower than some threshold. So this is a scheme that we call it trusted measurement scheme. And it actually contains two parts. The first part is there's a state commitment, meaning that the prover must prepare the state without knowing what measurements to perform. And there's the second part is honest measurements. So actually, this is not a new scheme, like a new setting, but like only a few of previous papers have mentioned this explicitly. Actually, this Bermuda-Vega et al. Paper has already given a verifiable quantum advantage scheme based on this IQP sampling problem in this state transmission or trusted measurement scheme. But in their protocol, quite a few samples are required. So this is their main drawback. And in this work, we propose a quantum advantage demonstration protocol, which is based on the same sampling problem as in the Bermuda-Vega et al. Paper, and requires either trusted measurements or quantum state transmission, and it achieves a reasonable balance between three nice features. And the first one is rigorous hardness guarantee, which is there because we are based on the same computational assumption as the Bermuda-Vega et al. Paper. And the second one is efficiently verifiability, meaning that the verifier in our protocol only need to perform polynomial time classical commutation. And the prover only need to prepare a constant number of copies of some state. So we call this constant sample complexity. The third nice feature is that we have near-term practicality, meaning that the prover in our protocol only need to perform some mostly analog commuting Hamiltonian evolution plus some global CZ quantum operations. And this global CZ here just means that there's a CZ gate that is controlled on one qubit but acting on all other qubits. So this is actually actually harder than just like analog quantum simulation, but it's still somehow near-term implementable, which is something we will discuss in this talk. So our work has two parts. The first part is the verifier strategy, or the verification protocol, which is inspired by the Feynman-Kitaev clock. And the second part is the prover strategy, which is just the experiment proposal in which we will use a echo trick. But in the interest of time, I might not be able to cover this part in detail. So let's see. The first part, the verification protocol, the overview. First step of the verifier is that the verifier needs to send some classical information to the prover. And this classical information are first, the classical description of the input state phi naught, and two, some instructions of what measurements to perform to the prover. So the first step of the prover is an untrusted step in which the prover needs to prepare NM copies of this single-step history state, where NM here is a constant value that is independent of the qubit number. And this history state here actually plays a key role in this Feynman-Kitaev Hamiltonian mapping. But here I'm not going to go through the Feynman-Kitaev Hamiltonian. I'm just focused on this very simplified version, which will be used in our protocol. So this history state is simply the superposition of the input state phi naught and the output state e to the minus IH acting on phi naught. And there is one more qubit. We call it the first qubit or the clock qubit, which is in the zero state if it corresponds to phi naught, and is in one state if it corresponds to the output state. Recall that the Hamiltonian here is just the same ZZ plus E Hamiltonian we introduced before. The second step of the prover is the trusted step. So in this step, the prover just measures each copy of the state as instructed by the verifier and reports the measurement outcomes to the verifier. The last step of the verifier is just the verifier calculates a lower bound of the output fidelity and compares that against the threshold fidelity. If it's higher than the threshold, then it has computational advantage. So here, this output fidelity is the fidelity of the output part of the history state. So it's only the second part of the history state. It's not the fidelity of the whole history state. Okay. Right. Now, you might be wondering why this history state can enable efficient verification. So the intuition is that compared to only having this output state, having the history state allows us to check the input state preparation fidelity and the Hamiltonian evolution fidelity separately and independently. So let's check the real state given by the untrusted prover, because the prover is untrusted. The state may be any arbitrary state. So we just use this most general model where alpha and beta can be any complex numbers, and phi in, phi out can be any n-qubit pure states. And in this presentation, I'll just focus on pure states, but actually all the results also apply to mixed states. So it turns out that if you can check the input state preparation fidelity, which is the overlap between the phi in state and the phi naught state, and if you can also check the Hamiltonian evolution fidelity, which is the overlap between the phi out state and e to the minus IH acting on the phi in state, then you can easily conclude that the output state, which is the output fidelity, which is the overlap between the real output state and the ideal output state, will be good. So this means using this history state, we just need to check these two fidelities independently. So first we check the input fidelity, which is quite easy. You just measure the first qubit in the standard basis. If you get 0, you just measure all system qubits in their corresponding basis of the initial state, and this will give you the fidelity of the input state preparation. For the evolution fidelity, this is actually the hard part. It's harder to check. So we're inspired by this Fermi-Kitaev Hamiltonian to design our protocol or strategy for checking this fidelity, where we consider an operator called O10. That is just defined as 10 in the first qubit and e to the minus IH on the system register, on the system qubits. And it turns out that the expectation value of this operator, when you acting that on the psi real state, will be directly related to the evolution fidelity. So this means that by estimating the value of this operator, we'll be able to somehow lower bound the evolution fidelity. But unfortunately, this O10 is not Hermitian. But the good news is that the expectation value of this O10 can be easily estimated for our Hamiltonian, because our Hamiltonian has some really nice features. It's just a ZZ plus Z commuting Hamiltonian. So let's first see the first part. 10 is just equal to x minus iy, so that's easy to measure. And then, due to the commuting nature of our Hamiltonian, we have a very nice formula for the second part of the O10 operator. So e to the minus IH can be simply written as a product of two parts. And the first part is simply the product of all of these I plus I ZGZK terms. And JKs are these nearest neighbors in the lattice. And the second part is just the product of I plus IZJ terms. So this means that if you want to get the value of this e to the minus IH, it suffices to just measure every system qubit in the Z basis, so you can get all the ZG values, and plug in the values into this formula, you get the value. So this whole process only takes ON complex number multiplication, so it's very, very efficient for you to do verification. So finally, we know how to measure O10. We know how to estimate the input fidelity. The other result, theoretical result of our work is this formula of the lower bound of f out, which is something that's just written here. So this means that if we want to estimate the value of f out to some constant precision, it suffices to just measure both parameters, the O10 squared and the input fidelity, to both of them to constant precision. And this can be done just measuring constant many copies of the state. So this justifies our constant sample complexity. So finally, to briefly summarize our protocol, it's quite simple. You just first prepare a history state, then you estimate the input fidelity and the evolution fidelity to lower bound the output fidelity. And this whole protocol only requires polynomial time classical computation and constant sample complexity. Now, I'm going to briefly introduce what is the prover strategy, which is basically how the prover can prepare the history state, because that's the only thing that the verifier requires the prover to do. So the history state is just shown here, and we can start from some easy to prepare initial state, that is the plus in the first qubit and phi naught in the second register. So we can observe that the single qubit terms, that are the single qubit ZI terms, can be all absorbed into the initial state preparation. So we only need to worry about these two qubit terms. So now we also observe that this lattice, this 2D lattice, is too colorable because it's a square lattice and only has nearest neighbor interactions. And we also have this very elementary commutation relation. That is, if you sandwich the zi zj by any xi or xj, you'll get negative of zi zj. So this gives us the idea of the circuit of preparing the history state. We can add CNOT gates that acting on only one color of the lattice before and after the ZZ evolution operator. Then we'll be able to produce this direction control state. That is, 0 state correspond to inverse time evolution, and 1 state correspond to forward time evolution. So once you get this state, by applying the Hamiltonian evolution in the forward time again, you'll be able to have the history state. Now, actually, as I said before, we need to apply the CNOT gates on like only one color of the lattice. That is quite a non-trivial half of the qubits. So it may be very hard in practice to implement this. So we come up with an easier solution. That is, we can use a global CZ gate plus some single qubit hallmarks before and after the global CZ gate on the qubits that we wish to run CNOT on. So the final circuit will be just showing like here. You can see we need to use CZ gates for twice, use Hadamard gates 4 times, and the evolution twice. We'll be able to prepare the history state. Now, I will also briefly talk about the experimental proposal, because we have known that in order for the prover to succeed, he needs to be able to do 3 kinds of quantum operations: unit time ZZ plus Z type commuting Hamiltonian evolution, and single qubit rotations, and finally a global CZ gate. So it's quite obvious that the first 2 are already available in many existing quantum platforms, but the last one seemed to be more challenging. But we in this work, we propose several schemes to implement that. And one scheme is called this BOSS scheme, and we also noticed that this there's a strategy that you can apply in this reconfigurable atom arrays to prepare this, to implement this global CZ gate. So basically, the BOSS scheme is that you have a BOSS degree of freedom in the center that is coupled to all the system qubits, and this will enable us to implement some global CZ interaction. So maybe the main takeaway from this slide is that, this kind of scheme is possible to implement, but it might need to be incorporated in the initial design of your physical platform. So this means that if you want to use the BOSS scheme to run our protocol, you might need to design your experimental platform from scratch. There's also this reconfigurable atom array idea. I guess I don't have enough time to cover, but we can talk about this after the talk. So finally, a summary of comparison. What did we achieve in this protocol? We can compare our protocol to others in terms of quantum classical resources spent. Like we require less samples compared to the Bermejo-Vega et al. Paper, but our protocol is slightly less practical because we have this global CZ gate. And our protocol is more practical than cryptographic proof of quantumness, but we require this trusted measurements, so it's not very computer scientific verification concept. And we have much more efficient verification compared to random circuit sampling because we just need linear time classical computation. And finally, discussions. You may wonder like how many qubits are required. In the worst case, we need maybe 3,000, which is pretty bad. But there's a trade-off between the uniformity of the Hamiltonian and the number of qubits. And in this case, maybe we can reduce that to like 100. So for the same reason, the noise in the measurements, because actually our protocol can only tolerate the noise rate in the measurement as 1 over n, which is pretty bad. But if n is not too bad, it's not too big, so this noise rate of measurement requirement will also not be too crazy. And finally, some future directions. It would definitely be very interesting if we can implement this idea in any experimental platforms, no longer is analog, mostly analog or digital. Also, we're also interested in whether there can be some simpler verification schemes for more general quantum simulations rather than just the commuting ones or very a little bit trivial ZZ plus Z kind of Hamiltonians. So this concludes my talk, and thank you very much for your attention.